unable to host because my laptop detects it's connected. It detects there's some input, but it just doesn't display. So last time I just called that guy and he rebooted the system or something, and it just started working again.
You can press system off. It doesn't display for some reason.
Do you want to swap out laptop really quick?
This is 4307, right?
What?
This is gate 4307, right?
207?
What's the room number?
Room number?
Say the number.
It's like that. It's like a 4. That one is 4401.
Yeah, she.
I can check right now.
Yeah, it's currently in, and the laptop recognizes it. Thank you for that. Oh, wonderful. It's showing now.
It is 4307. But,
Cool, yeah.
I see. Gotcha. Thank you. Yeah, you too. Thank you. That actually was very helpful. Okay. The stream started.
Yeah. Oh, is that? Oh, nice. Yeah. Oh, cool, cool. So Ryan has to post this on Piazza, I think. Is he? Should we?
We can go ahead and get started.
Oh, okay. Like I ideally need this, but it's okay. So.
Hey, Ryan.
It's posted. But is anyone monitoring the stream? Is it working? There's no, like, it's just, yeah. Yeah. So that makes sense before slides, and then you can jump in. Okay, that's fine. It's unlikely because I'm sleepy. Yeah. All right. So just to confirm, the audio on the stream is up, right? I have a. Okay, while we're waiting for the notebook to be shared with you guys, like this data that you're going to be using today. So let's just start with discussing what we're going to do. So this tutorial is an introduction to RNNs. We're going to have another tutorial sometime in the future where we really go into depth and discuss a lot more state-of-the-art techniques. This is just meant as a primer for yeah, 2 weeks from now, we're going to have a proper sequence-to-sequence tutorial where we go into a lot more detail. So this is just meant as an introductory primer to RNNs. So far, everyone has worked on homework 1, and maybe some of you have started homework 2. Let's hope all of you have. But so far, most of what you've been doing is dealing with fixed length inputs, and the inherent limitation in that is that real world data is really like that. Like if you take the example of speech, it's an arbitrary length sequence, and if you want to perform speech recognition, we tried to emulate that in homework 1 part 2 by having some context and a fixed length sliding window. But again, that's not the smartest way of doing things. It provides some context, but even then, you don't have any context outside the window that you choose, and you guys saw that quickly blows out of proportion. Like you can't have a context of 50 without really squeezing memory optimizations out, and like it's just not a smart idea. So RNNs sort of get around this limitation, and we're going to get into how and take an example sometime later. But before you learn to walk, before you run, you must learn to walk. So let's start with the random walk process today. So is the data on Ryan? Is the data on? Yeah. Okay. So there should be a link on Piazza with this notebook and some data. So I took the liberty of scraping some tweets, Donald Trump tweets from it. It's not representative of language, maybe, but whatever, it's fine. So there's a data set which I formatted for you. So it's clean data, all small letters, no special characters. So it's just easier for you to use today. So you guys can just download. I'll start stepping through this till then. So for those of you who haven't really dealt with RNNs or text generation so far, so let's not go into that detail right now. Let's just look at this, look at another way of solving this problem, how you do this statistically. So let's say you have a collection of you have a collection of tweets, which is a set of strings. So if I have to randomly generate text from it, so one way of doing that could be I collect statistics across characters, pick the most frequent character. There's going to be a probability distribution over the characters, and according to this distribution, I sample some letters and start generating text. So this process is sort of Markovian in the sense that you don't care about what you picked last time. It's a distribution, and you sample something from it each time. So evidently, this is not going to be a very smart way of generating things, but because this also does not incorporate context. So let's try to incorporate context by having strings of length, substrings of length greater than 1. Let's say we have a history length of 3, which means that I'm going to be looking at the previous 2 characters that I have generated in order to limit my search space for the 3rd character, and then pick it according to this distribution. So I have this is something I just put together for this class. This is by no means the most efficient way of generating things, and it might not work very well for larger things, but it's fine for now. So this is just a simple input function that I created, which returns statistics over the data according to a given history length. It's essentially a probability distribution over over the set of strings of length, history length, which in this case is 3. I have written a function which generates a next string given this string, and have a function which samples, which creates an output sample from this.
So let's say we have the file tweets.txt is a plain text file which contains some processed tweets. Let's step through this and generate a sample of length 50 with the seed OBA. And like this is the output. So it's English-y, but like it's not language by any means. So some of you might argue that Donald Trump tweets will not end up looking like English. So I picked up a string from Hamlet, like a small sample. And using the same configuration, I'm generating something which is closer to English, but we're not quite there yet. So if we increase the history to, let's say, 4, so the first line is going to be the tweet generation, and the second line is going to be a generated sample from Hamlet. So getting closer and closer. If you go to length 5, then I mean, yeah, it kind of works, but again, this is a random process. It's a Markovian generator where I don't care about anything beyond history length beyond this. So, and another limitation to the approach is, like, one might argue that what if I set a history length of, let's say, 50 or like 100, and that helps the context. But the issue with that is that at some point you go from generating to memorizing, and that's not what you really want to do in the first place. On top of that, with increasing n, you run into all sorts of difficulties with storage. Like, let's say you have a 100 length history with 26 possible characters, so that's exponential in terms of the vocabulary. So it's just going to blow up very quickly. And even if you hypothetically manage engineering a good thing, it'll still be sparse. You might encounter strings which don't really occur in the data. So there exists all sorts of techniques in literature to get around this, but none of them get around the fact that you need context and long-range dependencies, which is why we need RNNs. So let's go to RNNs.
All right. So, where is it? Alrighty. So, going to dive a little bit more into some of the models that you can use for actually constructing RNNs, and talk a little bit about how you can sort of see them build up from what you already know already. So what we're going to cover, basically what is an RNN, the backpropagation through time algorithm, which is the way that you train these RNNs, different sort of ways that you can use RNNs in your systems, how you can actually layer these RNNs together to sort of do the same layering that you've got in feedforward neural networks, types of RNN cells, and then simple ways that you can have these things fall apart if you use them correctly. So what is an RNN? So the idea is that it's exactly the same as a regular neural network, a feedforward neural network, but you have some connection that goes backwards. So this is just a traditional feedforward neural network. Hopefully this should all be familiar. You've got some input, some hidden layers, and then some output, right? So this is kind of what we've already all seen before. But this is kind of now getting into RNNs. So here we've got some input, we've got some output, but we've also got some hidden states coming in and out. This is still pretty much exactly the same as a regular feed-forward network. The only difference is that we've got these two extra values coming here and here in the hidden values. But for the purposes of thinking about this, it's literally just a set of zeros that we're concatenating onto the input. So we've basically just expanded the input and expanded the output. Right? So this should still be just a simple feed-forward network that you guys are already familiar with. Yeah, so let's say this is 0 and this is 0. So literally, it's just we're concatenating zeros onto the input, and we're calling it the hidden state for the purposes of this. Now, this kind of looks a little bit crazier, but this is kind of how you can think about RNNs coming into play. This is just a bigger feed-forward neural network. But as opposed to actually having zeros in the middle, now this is just another hidden node. and your output is selected as a extension of some of your weights in the middle, and some of the weights on the outside for the other one. This is the sort of RNN cell that you see people talk about. The idea is that this cell gets repeated over and over for every input. And so you're training the cell, you're not training this network. But you can kind of see that this is just a general feed-forward neural network, right? So you've got some input, you've got some zeros, you've got some input which is not dependent on this guy, but it's dependent on this hidden state. And then you've got some outputs which are, again, dependent, not dependent on anything, but come out of the neural network. The idea is that this kind of looks like a feed-forward neural network, right? Just in this structure. You've got some inputs going in, you've got some outputs going out. It's kind of the same idea. So in terms of so now, hopefully, are there any questions about that, actually? I kind of skimmed through it a little bit. Does anybody not get how that works? Yeah?
The output from the first cell, does that get fed back into?
This output 0?
Yeah.
No, so this is, I probably should have clarified this. This is, let's say that this is like a part-of-speech tagging task. So this is your input, and you're trying to generate a tag for that input, right? So the tag for input 0 is the output 0. And so once that tag goes out, it's kind of just your label. And then the input is, let's say, the next word, and then output 1 is the tag for that. If you wanted to do like sentiment analysis, this is the same kind of architecture that you'd use. You just would ignore, you wouldn't have these weights here. It doesn't matter whether or not they're actually getting output, you just wouldn't have the weights there. And so, yeah, if you wanted to do some other kind of task, we'll talk about that later. Does anybody have any other questions? Yeah.
Why there is hidden 0? There are already hidden layers, I think, in the cell itself, and then there is hidden 0 also.
So when you're first starting out in when you're first starting out in RNN, you're going to have your hidden, like this is just the neural architecture for it, right? So this is just the state, the structure of your network. But you need to be able to pass some amount of information between the cells so that they can keep track of context or the previous output or something like that. And so that's why we have these hidden values here at hidden 0, 1, and 2. When you're first starting a neural network, this hidden state is just zeros. So like if you hit the first word in this example, then you just have a zero, an array of zeros going in as input. Yeah. Yeah, sure.
So since we have this question, I think it's time to jump back to the notebook, and I have something which might help you figure out why we're doing something like this. So coming back to the example of tweets, so what we had right now was, let's look at the code step that I have. So this is pseudocode. It's not really meant to compile. I just want you guys to have a look at what we did so far. So in a Markov generator, we had a current state which I initialized by choosing the string OBA, Obama, or whatever. And then for some fixed length or number of steps, I generate an output. I have a new state. I replace my current state with the new state. So if you look at the function which generates a new state, it is simply, it just depends on the current state. It depends something new, and it replaces the current state. So that just kind of washes out what we have. And you are forgetting what was happening at the previous state so far, and you have to stop doing that to capture long-range dependencies. So consider instead this a small example of what an RNN might look like in the future. So if we have a memory state, and by initializing its self-memory state, like it's something which stays constant in the memory. And if you have a smarter process than just replacing, which depends on the current input and the current memory state, which updates the memory state, if you're able to capture something which incorporates both the input and the memory state, so you're able to sort of keep track of where you're coming from and what you're doing right now. So it incorporates both. So yeah, this is just and then you generate output according to that. So this is just a overall overview pseudocode kind of thing. So let's take a concrete example. It's still pseudocode, so it's not as concrete. But so if you look at, let's say we define the step to be something like this. So you have some input vector x, some output vector y, and a hidden memory state vector h. And let's say suppose I have this equation which defines the update step. There's nothing wrong with this. Like, it's something which depends on the input and the current state and the input matrix wxh, which is, and it also depends on the current state. The tan h is just there for kind of squashing values together, activation, and then you have an output which depends on both of these. So if you do this repeatedly, so you're kind of having a recurrent thing where you started off with something, let's say it's random or 0 or whatever, and then you know where you're coming from, you have an input, and then you take a step by modifying everything, and then your memory state sort of keeps track of all of that. So that's the idea, the idea behind what we're doing.
So does that gets your question? Okay. All right. So the idea, like Rajat was saying, is that you're training this cell. You're training the weights in these boxes, and then you're passing this memory along between the cells so that you can kind of keep track of your previous context as you're moving. You're training these cells not as an entire network, but each cell as sort of the same thing. So these weights are shared across the two, kind of exactly in the same way that we were talking about CNN filters getting trained before. So in terms of backprop through time, obviously, if you're training the same cell and you've got inputs coming in from different positions, it can get a little weird to think about in terms of how you actually want to do backprop. So it's similar to backpropagation as you're familiar with it, but there are a couple of little caveats going on with it. So hopefully this can kind of motivate that. So here is the just traditional feedforward neural network that you guys are familiar with this. We can backpropagate through this. It's not, this shouldn't be anything that's difficult. And here's that structure that we were just talking about before. So you've got some input, a couple inputs going in, a couple outputs going out, and then some hidden values going along. But this kind of looks like a feedforward neural network if we just sort of rearrange it a little bit. So we've dropped the two input hidden states, or the input and the output hidden state, just because those are all zeros, and for the sake of the notation, we're dropping them. But here we've just got two inputs on one side, two outputs on the other side, and some hidden representation in between, right? So this is almost exactly like a feedforward neural network, but we're just going to be backpropagating, some weird connections as opposed to having a fully connected layer or something like that, right? So that's kind of the idea for backpropagation through time. Is you're doing regular backprop. You're not doing anything different in terms of the algorithm, but the idea is that you're going to be unrolling this network. You're going to be unrolling this network across your instances, right? So you unroll your network, you take each cell, you kind of just attach it to each other. The weights are all the same, they're all fixed, but you backprop across all of the labels that you've got as one big function, or one big loss function for each label. And then you get the gradients for each one as if this were one big feedforward neural network. You get those gradients, and then you average them together, and then you update the gradients in your cell as the average of all the gradients, right? Does anybody have any issues with that? Any confusion? Yeah?
When you're saying you average all the, you're saying like, okay, considering those two sort of boxes,
yeah.
You have the same cells in each one.
Yep.
You're saying we find the gradient as if we were doing normal backprop, as we had before. You find the gradients for each of those like layers, right? And then some of those layers are duplicated.
Exactly.
Right. So then you take the average of those ones and apply.
Correct.
Okay.
Yeah, so just to parrot it back to make sure that everybody else got it. So the idea is that even though because these two cells are the same weights, and because because the weights are tied between the two, you can backpropagate this as if it were a full feed-forward network, and you could do it. You could get a gradient for the weights coming out of coming into output 1 and the weights coming into hidden 1, or rather the weights just before in the layer just before that. You'll get those weights, but they'll be slightly different values because the inputs and the hidden states are going to be different. When you're actually training backprop through time, you just want to combine those two and then calculate the gradients for the entire cell that way. So you're basically just doing a feed-forward neural network. It's not that complicated. The main trick is that you need to sort of unroll your network to make it into a big feed-forward neural network so that you can then do the regular backprop through it. Are there any questions? Yeah.
When you say rolling it out, how many cells would you typically have as you're doing this? Is it dependent on like how far back you want to remember?
And so it's actually entirely dependent on how many input samples you have. So this is word 1, this is word 2, and you could go back all the way to word 0, right? Or you could go back to some arbitrary thing that you've defined, right? So if you only want your network, for whatever reason, to train back 5 hidden states, you can totally do that. But if you would rather have it go all the way back to the beginning, which is typically what happens, you can do that too.
So even in like a corpus of Hamlet,
Yeah.
this network would be the entire, like a cell for each word of the entire.
Oh. So in a corpus like that, typically it's divvied up by sentences.
Okay.
So you do like words in a sentence, and then you do, there are models that are like hierarchical, so you could do words in a sentence and then sentences in a document or something like that. But that's the main idea. Do you have a question?
So, for input 0, output 0 will be the actual labels or whatever, and then you calculate loss. And for output 0, you just backprop 1 cell, and for output 1, you backprop 2 cell. Is that what happens? Means what happens to output 0?
Okay, so when you're doing backprop, so the question was what happens to output 0 if you've only got the labels for if you've got the information for output 1, right? So the idea is that you have the labels for both output 0 and output 1 if this is a sequence, right? So for input 0 and input 1, let's say that it's a 2-word sentence and you want to do part-of-speech tagging on the 2 words, right? So the idea is that you've got 2 labels in, 2 labels out, or 2 inputs in and 2 inputs out. So supposedly, if this is a training instance, you've got labels for both input 0 and input 1 and output 0 and output 1, right? So this is just treating it like a regular feed-forward neural network. So you've got your, let's say, part-of-speech for output 0 and your part-of-speech for output 1. You calculate the gradients for output 1 going into this network and then going back all the way. And then you've got your gradients for output 0, but only going into these hidden cells. So you're kind of just treating it as a regular feed-forward neural network and then just with some weird connections to make it work. Did that answer your question?
Yeah.
Okay. Oh, yeah.
Question from the stream. Someone's asking what the relationship between output like 0 and hidden 1, or in general the output and the hidden values coming from the same cell.
Gotcha. So the question was, what's the connection between output 0 and hidden 1?
Yeah.
So since this is kind of just a notational thing for the purposes of this slide, the two are not necessarily dependent on each other. They're likely going to have some interaction, and we can talk about some neural network architectures, some types of cells that will be. I think, yeah, that will probably be. But yeah, you could have these two be completely disparate, or you could have these two be entirely dependent. You could make your hidden state your output state if you wanted to.
In one example, they're both linear functions of the same value.
Yeah, so yeah, they could be linear functions of the same value is a great example of when you'd have an output and a hidden state where the bias may be different, but the function is still the same thing that's going on. Yeah.
Would you please explain how the mini batch will work in this model?
Oh, how mini batching would work in this model? Yeah. They've all got different shapes, and yeah, this would be, I think the professor is going to cover, we're not going to cover this in this slide, but in this class, but I believe the professor's slides are going to go into it in enough detail so you can hopefully get around it.
Second question is, it seems like the later output, the more information you will carry.
It seems like the later the output, the more information that you will carry. That is true, yeah. So, I mean, when you're doing, yeah, so as you start doing this this process all the way through, this hidden state is going to need to be supposedly representing everything that came before, and so there's going to be some information loss because hidden 1, let's say, is a fixed length vector or something like that. And if you have a sequence length of infinity, there's no way you're going to be able to contain all that information. So there's going to be information loss, but this is more of just a way to try and mitigate that as best as possible. So if you have some dependency that's really important for classification all the way at the beginning of your network, this hidden state, even if your length is infinity, can hopefully carry some amount of that. But you're going to run into problems with that, and we'll talk about that in a little bit. Are there any other questions? Does anybody not get this? Anybody just totally lost? All right. Cool. So there are a couple of different ways that you can actually do this. So there's the one-to-one. This is just your standard feedforward neural network. You could use an LSTM cell or the cell that we just defined to do a regular feedforward neural network. There's nothing stopping you there. It's a possibility. The other one is the one-to-many. So this is, you get a single input, you get many outputs. Then there's many-to-one, you get a single input, or you get multiple inputs, you get one output. Many-to-many, this is like sequence-to-sequence. And then the other one is many-to-many, but it's sequence labeling. So how is the, this would be like a part-of-speech example. So simple feedforward neural network. Given an input, predict a sequence of outputs. So this is like image captioning. So you get an image in, and you want to predict a sequence out. So you want to give labels to the image. Then given a sequence, predict a single output. That's backwards. So you've got sequence in, you want to get something out. So this would be like sentiment analysis or abuse detection or something like that within text. So this is machine translation or sequence-to-sequence dialogue modeling. So given a sequence in, you can predict a sequence out. This is all kind of hand-wavy, but the idea, jumping all the way back to all those slides before, is that you can do whatever you want with that initial hidden state. So we were talking about getting an output for each LSTM cell. You can do that, or in this case, you could just ignore those up until the last minute, and then keep generating until you hit some end condition. So the LSTM has generated enough, and you're done with it. Or maybe the token that you've generated is some stop token that once you reach this token, the process is over. And then this would be like part-of-speech tagging, there are a couple of other things you could do, but part-of-speech tagging is probably the best one to think about. There are different problems. RNNs, different structures of these things can be used for different things. I know this is kind of hand-wavy, but we're going to get into it in a little bit. Any questions about just the general structure? Yeah?
Can you equate this at some level to like a filter with feedback?
Can you equate this in some way to a filter with feedback? Yeah, almost exactly. It's the exact concept. So this could be like just like a CNN filter, and you're just giving some feedback to the cell.
For those of you from signal processing, this is an infinite impulse response filter, as opposed to convex being a finite impulse response filter.
Yeah. So to repeat the professor for the stream, this is an infinite repulse responsor, impulse responsor, excuse me, versus a finite one, which is what CNNs are. All right. What? What'd you say? I can't hear you. Okay. So in terms of layering for neural network for RNNs, this is kind of the structure of the layers. You can have additional layers within those cells like we were talking about, but that's kind of the cell. If you want to layer the network vertically, you can do that too, and this is kind of the structure that you want to do for that. Typically, this layering process doesn't go more than 5 or 6 cells deep going down. You can do higher, but these things can get really dense just because you've got a full neural network in in part of it, and then if you're going vertically, it can get really, really, really big, lots of parameters. There are a bunch of different things that you can do. So you can change the granularity of each layer. So like maybe this top layer will only deal with every 2 or every 3 in the bottom layer or something like that. So you can concatenate inputs and send them into a sort of hierarchical layer, one up. You can also change the order and direction. So hopefully, maybe you guys have heard about the hype regarding bidirectional RNNs. So you know, one of these layers goes one way and the other layer goes the other way, and you kind of just like zigzag your way up. So that's one way of doing it. That doesn't always work when you have like, if you're trying to do classification on the fly, but it's a starting point. Yeah, hopefully this makes sense to you guys. Is there any questions about how you'd actually layer these? Yeah.
Question of the stream is just what if green blocks where the in outputs, like point out where the input goes in the output block.
Yeah, sure. So the green is the hidden cell that we were talking about before. This is the hidden state being passed, and then this is the output of that hidden cell. So the output of the hidden cell gets fed as the input to the hidden cell, or the output of that RNN cell gets fed as the input to the RNN cell one layer above. Hopefully that answers the question. Yeah.
What would be the intuition for stacking them up like this? Are you trying to capture like patterns that are close temporarily, and then you want to expand and aggregate over more remote things? Or
Yeah, sure. I guess Rajat's got a good answer for that.
Yeah. So we were going to come to this sometime during the notebook, but I'll just go to it right now because of this question. So just to refresh context for everyone, we started off with a Markov generator. Then we talked about, in pseudocode, we talked about how we could potentially do this in a smarter way. And a small tangent, which I must get to before answering your question, is that, I mean, Tom kind of covered this, but just to make sure. So this method works with arbitrary length sequences because at each time step you have some input, some current state, and you combine. And you can do that as many times as you want. So this is just like a Wikipedia image that represents that for a single layer. But there's no reason for you to restrict yourself to this. So for example, you could so instead of having just one recurrent layer, you could, so this is what we defined in pseudocode. We're going to come to a formal definition later on. But if you do it as a step of one and then have another step, that's kind of the idea of stacking, which we use so far. So it's exactly the same, except that the thing that you're stacking is recurrent in the history. So and moreover, that's not like stacking is not the only thing you can do as well. You can do anything which, as long as you're able to compose the network. So like I picked this example from a paper that appeared in EMNLP 2013. It's a PhD student from Stanford. So they did some sentiment analysis for movie review data sets. Typically, what people had been doing so far is like you have a flat input sequence, and at that point, people had started doing bidirectional, so that if you go, like each word has some previous context as well as some future context. So for example, if you're talking about a sentence like, I really like this movie, but it had something which made it unrealistic, so I wouldn't recommend it. So the first half of the sentence is kind of positive, but then there's a but. So how do you incorporate things like that? So they sort of split the sentence into the parse tree, and they came up with a very smart way of combining things at each node. So all the RNN cell has to do is combine things. Like given an input and a memory state, it sort of combines. So you can compose things up. So when you go up the tree and like you go up from this first half of positive and second half of negative, so that kind of captures. But that's not the point of, that paper is not the point of this recitation. The point is that you can do anything you want. There's no reason for you to restrict yourself to a flattened, linear, single layer input.
thing that I would throw out there in terms of intuition as to why this would help. There's a great paper by, I think it was Chris Dyer, who found that if you compose these networks, these layers, in a way that resembles a parse tree, you can get very good results for different tasks. So like if this, if you find that these RNNs are detecting that you're dealing with like a noun phrase or something like that, then you can combine them in a special way and sort of mimic a parse tree as you construct your network. It's kind of a weird way of constructing an RNN or like a layered network on the fly. But again, as you're training cells, you can kind of do whatever you want with this. Are there any other questions? Yeah.
What's the initial input for the most left part?
So what is the initial input for the most left part?
Green.
Oh, this guy?
Yeah.
So this would be, let's say, the first word.
Yeah.
And so words, right?
But there is error input from the left.
So he's speaking about initialization, so that is a learned parameter also.
Yeah.
0.
Oh, yeah, like the input to the hidden state? Yeah. So when you first start training, that could be, that's typically a vector of zeros. But as you start training, you can offset that with a bias, and so it becomes a learned value. Yeah.
So you mentioned that we can use these to construct, like using the parse tree, you can construct the SSTM layer, like for each training instance, I suppose. So
Yeah.
what happens at the test time, like given a new sentence, how do you use that training?
So like when you're constructing these things hierarchically?
Yeah.
So the question is, when you do something like hierarchical networks, where you have cells on the layer above that are potentially at weird offsets or something like that, how do you actually evaluate that? That's a good question. I don't know if I have a solid answer for you. I know they go into the detail in the paper, but I would imagine that you're just evaluating on your final. This is a situation where you'd be evaluating on your final label, and once you get that label, then you can just backprop the error down your network by unfurling this. Does that kind of answer? I know it's kind of a hand-wavy response. Okay. Sorry. Any other questions? All right. So common types of RNN cells. This goes into the math a little bit, but just for the sake of time, since I know we've got more notebook to cover, I'm kind of going to breeze through it. And you can look at the slides once they get posted, and hopefully the stuff there will all make sense. So this is just a dense cell. You can put a standard, like a feed-forward neural network structure into an RNN cell just by attaching some hidden input and hidden output. You can call it an RNN cell, and as long as it's feeding back, you're all good, right? So that's just a dense cell. Then we've got a gated recurrent unit, and this is a little crazy to think about. But this is your input xt, and that's your hidden state from the previous node, right? And then you've got your hidden state and then your output on the right. So this is an instance where your hidden state and your output are exactly the same thing. And your hidden state from before is the same thing as all the way back. There are a couple of weird things going on here. So these two sigmoids and that tan H are a full neural network sitting inside this cell. So you have 3 neural networks, some point-wise multiplication, and that's that -1 is also a point-wise multiplication, and then some addition to sum it up. The point of this is called a gated recurrent unit, and it's called a gated recurrent unit because these neural networks on the inside are kind of determining how much of the input from X in the hidden state to let through into your unit. That's kind of where the word comes from. The other thing to think about is that because these are full neural networks sitting inside, there are tons of parameters that you could be tuning with these things. So you could be training. You could be choosing, the size, the layer and the layers width, and the shape of all of these networks as you're training this thing. You could be choosing weights and all other kinds of things, regularization methods, the world's your oyster kind of thing. So there are like tons of hyperparameters to these kinds of networks. Most of the Most of the libraries tend to hide these things from you because there are just so many, but there are ways to get at it. Yeah, we're going to dive into the math a little bit. Oh yeah, the gates are neural nets. This is the math for it. We're going to skip it. It looks intense, but it's basically just doing a W transpose X dependent on some inputs, which are the hidden state and the input to your network. Yeah, if you want to look at it, it's there, but don't worry about it too much. The other thing to realize is that since this is all differentiable, we can backprop through it, so there shouldn't be any issue with that. This is an LSTM. So the LSTM is kind of an extension of the gated recurrent unit. Again, we've got all these nonlinearities here, which are neural networks. You've got another tanh up there, which is just doing a pointwise tanh on the input. Yeah, and you've got cell inputs and hidden inputs and outputs. The other thing you should note is that there's this new thing called the cell state, which is just something that gets pushed along the network as you're going through time. The idea with this is that if you're pushing something through without giving any crazy nonlinearities or feeding it through a neural network or something like that, then the gradient is pretty stable throughout the network. So this is, these networks were introduced as a way to try and solve the vanishing gradient problem, or at least a way to try and mitigate it. So the cell state input and the cell state output are not doing any crazy nonlinearities. They're just doing addition. So the gradient can get passed very easily through it. Yeah. The math is there. It's intense. But yeah, the thing to recognize is just you're doing neural networks on the inside of these things. Like I said, tons of parameters to deal with. But yeah. Common pitfalls. Yeah, because there are so many parameters and because there are so many different ways to tune these things, you can overfit incredibly easily. These networks can really learn your training set very quickly and overfit on, memorize the training set as opposed to actually learning the underlying stuff. And then because backpropagation through time generates really huge neural networks, if you unfurl it, you get a really deep feedforward neural network. Then you can get the vanishing gradient problem. That can become a real big issue because just the networks are so deep. So having things like the gated recurrent unit or the LSTM passing its cell state, there are ways to mitigate it, but it's something to consider especially if you have longer sequences. All right, are there any other questions? Yeah. So they call it forget gate. So the name of LSTM is a long short-term memory cell. They call it the forget gate because you've got some hidden input and you've got some regular input, right? And then you're putting it through some sigmoid, and the sigmoid's going to squash it between 0 and 1. So you're going to be multiplying everything by, this is a neural network, so the output's going to be maybe a weird shape, but you're going to be forgetting some amount of your input because it's multiplying everything by 0 and 1. Right, so if you're multiplying everything by 1, then you're forgetting nothing. But if 1's coming out of that sigmoid, I did a kind of poor job of explaining it. Let me try again. So here you've got, this is your forget gate right here, coming out of your hidden state, going into the first sigmoid, and then going up into the multiplication, right? So there's going to be a value coming out of this sigmoid, which is going to be between 0 and 1. That's going to get multiplied by the cell state, and that 0 and 1 value is the forget. If the output of that network is 1, you're not going to forget anything because it's going to get multiplied by the cell state is going to get multiplied by 1, and the cell state's just going to pass through unhindered, right? But if you multiply by 0, then everything's going to get forgotten from your cell state. So that's determining how much of your cell state you want to forget. Does that make sense? Yeah.
So for the aggregation functions, did you ever change them, or were these
This is the published example. I think people have messed around with trying to change them. I don't know the exact results. I could foresee something like you want to actively forget something, like you actually want to do the backwards thing, and so you could change that sigmoid to a tanh and do potentially negative pointwise multiplication. This kind of intuits well. You can, they're hyperparameters. You can do whatever you want. Yeah.
You're saying about the cell state.
Yeah.
It's better for to upload the longer before, right?
Yeah.
Can you provide some information about what the difference are between the cell state and hidden state?
So the hidden state and the cell state. So the the hidden state is going to be a combination of your input, right, and the sigmoid going into the multiplication of your cell state, right? So they're going to be a combination, but the idea is that your cell state and the hidden state are, similar values, but this cell state can backprop all the way without hitting any crazy nonlinearities, just hitting multiplication and addition. The main point was just to get your gradient potentially all the way from the front of your network all the way to the back. So you could think of your cell state and your hidden state as just two different hidden values, but the main point was to get all the way from the start of your network, from the end of your network to the start, uninterrupted by something like a sigmoid, which would cause your gradient to start dropping to 0 or going up crazy. Does that help? Yeah. Okay. Any other questions? No.
So could we go to the slide with equations? Actually?
This one?
And suppose let's take the forget gate. And so what you were saying is that you have the second state of cell, and actually you kind of can fit the entire network through it. Or not really. So would the product of W and then the hidden state in X be actually like a simplified version, and you could have a multi-layer something in there?
Oh, like in here?
Yeah.
Yeah, you could put like you could put like a 10-layer deep neural network in there. It doesn't just have to be a perceptron or something like that. So yeah, the question was if you can put a full neural network inside of these nonlinearities that we've got here. The only thing that I would call out is that you've also got this tanh pointwise operation that's going on the output gate, but that's a pointwise operation. The yellow boxes can be full neural networks with any shape that you want. It could be 10 layers deep. It could be some crazy highway network. It's whatever you want to do, as long as it's got a sigmoid and or a tanh on the outside. Yeah. And so I'll let Rajat jump back to the notebook.
Yeah, and this is how it works. Like, can confirm. Okay, so back to the recitation, the notebook. So just a quick context reset for everyone. We started off with the problem of text generation. We started using statistical methods of generating text. We understood why this is not able to capture long-range dependencies, which is sort of a primer for why we need such complicated structures in the first place. We saw that the step where the Markov chain generates the new state is sort of washing out the previous information, and therefore we should have a smarter process which uses something like this, which is dependent on the current input and the current hidden state. So, and we saw that we can combine things in many different fashions. So yeah, so let's take a concrete example now, and like this is just a very simple time series prediction task that I've adapted for this recitation from the PyTorch examples. So you generate some random collection of sine waves. So you generate some collection of random vectors which all start at different points. So that's like a sine wave with different phases, and then you generate all of them. So this is what we're going to be using to generate, to learn and then generate the sequence. So we're just using a simple LSTM cell. So all of the math that you use, it's good to understand and know, but this is what you're going to be using, and notice this does not involve any equations. You just define a cell. So an LSTM cell is probably not the most efficient way of doing things because it doesn't parallelize as easily. There's better ways of doing that in PyTorch, but for the purpose of this recitation, it's fine. So LSTM's long short-term memories were were created by Schmidt, who were obviously, and it's the idea behind the name is that you have long range dependencies as well as short range dependencies. Why we came to this complicated structure in the first place is because, so if you look at a vanilla RNN where you don't have all of these gates interacting with each other is kind of, so we're not going to go into that during this recitation, but standard RNNs have a problem where theoretically they're capable of remembering things in the sense that there's nothing washing out information, but let's say 10 steps back, you had something and you passed it through 10 multiplicative steps, squashing through a nonlinearity. That's not really going to persist. So the issue is that you're going to have like the vanishing gradients problem. Professor will go into it in further detail during the RNN lectures. So the LSTM paper sort of got around this by having a constant the multiplicative units sort of depend on the input. So you have a forget gate if you really need, if the input you have needs to replace the previous hidden state, you do that. If there's an input which perturbs the current state too much and will not be informative, you don't add it to your current state. So things like that, like this is kind of superficial. Professor will talk in more detail, but this is the idea behind why we're using such a complicated setup. So as we saw that you can just stack, so let's stack two LSTM cells. So this is the input is a real number, and the output is a real number. So you have a mapping from the LSTM hidden state to a single real valued output, and you define your forward prop. So because we're going to be predicting the future steps at some point, there's a separate portion for future, which by default is 0 unless you call it for this thing. This is just a this is just a plotting function. So you create some input, you split it off by taking one slice as a test sample. Notice that the the input and the target is staggered, because what you have at this step is going to be predicting the, if you have an input at the current step, you're going to be predicting it at the thing. So you have to separate this. I also picked this specific example because it's just quick enough to go through in a recitation, as well as it uses a different optimizer. So you guys have been using variants of SGD, Atom, all of those things. So this, the LBFGS, the limited memory, Goldfarb, Shannon, something like, I forget the exact details, is a numerical estimation method for the gradient. So the idea is that you have a smooth function that you want to minimize over some real values, and it's called in a different way because so how it works is that it recomputes the value of the function repeatedly. So you define what you used to do separately as a closure, and you pass it to the optimizer, and it takes care of that. So I just thought it might be interesting for you to have a look at how a different optimizer might work. So so this is just there, like it's you don't have, it's a solved recitation. You don't have to really do anything for now. So this is going to run for some epochs. You can try it out, and I can just I can just show you what it, after 10 iterations, this is kind of what it looks like. The solid line is a sample test input, and the dotted line is what the model tries to predict after that. So RNNs are really good at time series prediction tasks in general, so I just picked this example. And
what's the intuition why the amplitude shrinks there?
To be honest, I'm not too sure, because like I don't know what I haven't tracked what the hidden state is doing, but
I can give a hand wavy response, which is that the peaks I can give a hand wavy response, which is that the peaks of the predicted is at the same height as the initial input. So it might be getting biased towards that height across the average, but I'm not sure. Does the process have to be recurrent for time series data like this? Is that what you're asking? It doesn't have to be. Yeah.
Because it's easy to generate. So the question was, does the data have to be periodic?
No, actually the question is, does the data have to be ergodic? So would you expect the same pattern repeat over time? Or would you expect changes in the variance and the mean, and you don't have to do anything to address it?
Okay.
In the typical time series and statistics, you would not feed something like that. You would stabilize the
Yeah.
variance and the mean.
Yeah. So.
That you can actually compare the data pools.
Yeah. So I believe you can do it for like, you don't make the assumption that the mean or things like it's not constant, and you can use it for a general time series, like if you have something like, but yeah, I think there's not you can do that as well, like you don't have to make any specific modifications for that to work with your series. So, other questions? All right, cool. Fun fact to end the lecture is that LSTMs are Turing complete. So, because like the intuition is that you have a memory and you have something that's writing to it and reading from it. Of course, intuition is not proof enough. There is a formal proof out there, but like it's really cool that you can do a lot of things with. It's a really cool model that you can do a lot of things with. So, right. Is that, yeah?
So, in the code you showed, so you have used like LSTM cell. So, there's one LSTM also, like what's the difference in Python?
So, the question is that the code uses an LSTM cell and PyTorch also has an LSTM. So, what's the difference? The difference is that the LSTM cell is a standalone cell, and Ben might correct me on this, but I believe the LSTM, it's not the LSTM cell, the LSTM is able to parallelize this over the cells by default.
One of the big differences is that LSTM uses CUDA and it's like 10 to 20 times faster than this.
Yeah, so Ben
You can't modify this.
yeah, Ben adds on that the LSTM uses CUDA and is like 10-20 times faster than an LSTM cell, but LSTM cell is just easier to look at and manipulate. So if you have variable length inputs, it's easier to use an LSTM cell because you don't have to care about other inputs, which are, you're only processing one sequence at a time. So it's easier to visualize, but LSTM is faster because it uses CUDA. So. Right. Further questions? Anything else?
Just a little comment. It's like the prediction of the sine wave looks pretty poor.
Yeah, I mean, you can train it for longer. You have the code. This is just some. So I just picked 10 for the 10 epochs for the recitation, and this is what it'll look like after 10 or 11 epochs. So.
In terms of the training data, I guess it depends on what's the actual problem. Are you giving it a set of 10 words and telling it to predict the 11th word? Like, how do you generally structure the training data for something like that, or for different types of?
So the question was, how do you generally structure your training data depending on your type of problem for these kind of networks? In the case of a classification problem where you're classifying each word, your training data is going to be exactly the same length as as your input sequence. And when it comes to actually doing backprop, you're going to get all of your inputs lined up and you're going to get all of your outputs lined up, right? And you're just going to do the backprop by unfurling your network. When it comes time to do something like a labeling, like you get all your words and then you want to do like a sentiment value or something like that, then you don't have all the sequences don't align obviously. So you're just gonna either completely ignore, like not calculate gradients for the inputs coming, or for the outputs coming out of each cell, and then only deal with the gradients coming out of the last one, and then backprop that error through. If you have something like a sequence-to-sequence method, then it becomes a whole bag of worms, and trying to determine how you actually calculate your loss on a sequence is a research area in and of itself, and I think we're going to have a recitation on that topic specifically. Does that answer your question? Yeah. Okay. All right. Any other questions? How many feel like this? Like they're more lost on RNNs after this? Oh yeah.
Question I'm not too certain what it means. Is there some information reduction in the LSTM network? I mean, is there something like the autoencoders will?
Is there some information reduction in the LSTM network? Is it similar to autoencoders? Is that kind of? So you can use an LSTM as an autoencoder. So you're generating a vector representation as as your hidden state. So if you want to put that hidden representation into another sequence which attempts to generate the output, or into some other type of network that attempts to generate the output, you can totally do that. There is going to be information loss, obviously, because you're trying to fit a potentially infinitely length sequence into a fixed length vector. So there's going to be issues with just loss of information in terms of fitting series into fixed lengths. But depending on how much data you have, and depending on how big you want to make that hidden state, you can potentially handle it well. It depends on your training data. Yeah, attention is a great way to trying to solve. Attention, yeah, there's a great paper called "Attention is All You Need." If I'm going to throw it out there because it's amazing. But we didn't talk about attention here. Yeah, are we talking about that in a recitation? Yeah, yeah. Mm-hmm. Yeah. So in I think three recitations from now, we're going to cover attention. CTC, which is a sequence-to-sequence method, we're going to talk about next week, and then the week after that, there's going to be a recitation on visualization of neural networks, and then we're going to talk about attention. All right. Any other questions? Comments? All right. Guess that's it. Thanks, guys.